Hello, this video is on logarithmic functions. We're on a long journey through James Stewart's calculus textbook. We're in chapter 7, which is on inverse functions. And the third section is on a particular kind of inverse function, namely logarithmic functions. You may have heard of logs before. I've got some out in the woods next door. Anyway, logarithmic functions. So in the previous section, we've looked at exponential functions. Exponential functions are where the base is a constant and the variable is the power. Whenever we have a to a constant to a variable power equals x, that's an exponential function. The log function, logarithmic function, is the inverse of that. And so a is the base, right? Now, the log is the power. So when I ask what the log of something is, I'm asking to what power must we raise the base in order to get this number, which is x. So let me give you an example. 2 to the third power, so 2 to the third power is 8, right? So if we were to say what is the log base 2 of 8, we're asking to what power do we need to raise 2 in order to get 8? And the answer is 3. So all the same elements, but in a different configuration. And these are inverse functions. We can tell they're inverse functions by looking at this homegrown graph. It's also behind me. So this is the exponential function. And of course, the assumption here is that a is greater than 0, that the base is greater than 0. I mean, greater than 1 for all of these, right? So this is the exponential function. So if we take a mirror image of it across the diagonal y equals x, we get the inverse function. And there it is. So the inverse function is the log function, right? Now, all logs, no matter what base we're talking about, pass through the point 1, 0. Why is this, you ask? Well, it's because the power, y, to which you raise anything of x to get, so the power to which you raise anything, the power to which you raise any x in order to get 0 is 1, okay? So the power you raise any base to get 1 is 0, okay? Remember, the log is the power, so y is giving us the power. So the power of 0, anything to the power of 0 is 1. So everything's going to go through this particular 1, 0 point if it's a logarithmic function. Okay, well, let's go back. Cancellation equations. These are very useful in doing certain problems. You may look at certain, if you're like me, you look at certain problems, you think, what in the world, how can I do that? Well, using these little tricks might be one way to do it. So the log base a of a to the x is x. It's like, have you ever done that thing where you do the string and and it goes away? That's what happens when you raise a to the x. When you take the log base a of a to the x, it cancels out. By the same token, if you raise a to the log a of x, you get x. It cancels out. And so this is a very useful thing to do, especially when we get to natural logarithms in just a second. Don't go away. Okay, cancellation equations. What are some of the properties of logarithmic functions? Well, they're no big surprise given what we saw with exponential functions in the previous video. So if you take the log base a of two things multiplied by each other, that's the same as log base a of the one plus the log base a of the other. Ta-da! Just like we saw with exponential functions. Similarly, the log base a of two things divided by each other is the log base a of the top minus the log base a of the bottom. So again, these should look very familiar. Here's the third one. The log base a of x to the r power is r times log base a to the x power. Okay, yeah, and there you have it. These are some basic properties of log functions that may be helpful because you may look at a certain problem and think, I can't handle this problem as it stands. But if you put it into some equivalent form, suddenly the problem can become easy. Not always, but sometimes. All right, so what about the limits of logarithm functions? I knew you were asking this. So the limit as x approaches infinity of the log base a of x is infinity. And this makes sense because the curve, and I have to do it backwards, so I hope I'm doing this right. As the curve goes this way, it goes to positive infinity. It doesn't go real fast toward positive infinity, but as the number goes bigger, it goes toward positive infinity, okay? Now here's an interesting one. If you approach 0 from the right side, um, the limit is going to approach negative infinity. Now let me just show you on the graph, because you can see this really easily on the graph. So as you approach 0 from the right, it goes to negative infinity. Okay, and as you go toward positive infinity, you're going to eventually get to positive infinity. It's going to take you a while, but you'll get there eventually. So these limits make perfect sense given the way the graph actually looks. Okay. Now, as you also see, the y-axis is going to be a vertical asymptote for y equals log base a of x. We see it right here, right? There it is. Because the further you get down, you never get to 0, but you go to negative infinity as you're headed toward y. So the y-axis is an asymptote on the left side for the logarithmic function. Okay, now if I was dividing this up into part 1 and part 2, this is part 1. We're now done with it, having to do with logarithmic functions. Let's look now at a very specific logarithmic function, namely the natural logarithm. The natural logarithm is the log-based e, 2.718281828, blah, 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 blah. We looked at the natural logarithm in the previous section. It is a number that God seems to like. It is an irrational number, which I don't think means that God is irrational. I just think it's above our pay grade. But anyway, the logarithm-based e of x is abbreviated as the natural log of x. Now, I will say that there are some textbooks that when they say log of x, they mean natural log of x. This is very confusing. Just know what textbook you're in and when the logarithm notation actually means natural logarithm notation. I find this very annoying myself. And this is only 2 letters as opposed to 3, so why not use the ln? But anyway, I'm not a mathematician, so I don't get a say. But if we take the inverse relationship and we put it in terms of e, this is the way it looks out. So if we have the e to the y exponential functions equals x, we're basically saying that the logarithm-based e of x equals y. The log is the power, but we abbreviate log as ln for natural logarithm. Okay. Now, remember the log-based a of a to the x cancels out, and so the natural log, which is the log-based e of e to the x, is going to cancel out, and we're going to get just the x. Here's the other cancellation equation. If we raise e to the natural log of x, we get x. These are very helpful to know, because there's going to be a number of problems, and you can see these in the examples that James Stewart gives in this chapter. There's going to be some situations where the way to solve the equation is to take the natural logarithm of both sides of the equation. So keep that in mind. And of course, the log-based e of e is 1. The natural log of e is 1. Okay, natural logarithms. This is basically the same stuff we said with regard to logs in general, applied to the natural logarithm. This is very important, this change of base formula, because calculators use this to calculate a logarithm that isn't nice. So when you have strange logarithms, and by that I mainly mean strange bases, log to the, 2.7. This formula allows calculators to calculate logs of any base and so forth, pretty much. I mean, a wide variety, let's say. So the log based a of x equals the natural log of x over the natural log of a. There's a nice little proof of this in Stewart's book. It's not that hard. I'm not going to give it here. I do things by request, so if you want to put in the YouTube comments that you'd like me to do a video on the proof of this, I'm always glad to try to do those sorts of things, but I'm not going to. It should be fairly understandable. And again, this idea of taking the natural logarithm of both sides is very useful. Now, the limits are going to be exactly the same. So the limit of the natural log as x approaches infinity is going to be infinity, and then the limit as you're coming towards 0 from the right of the natural log is going to be negative infinity. Nothing unusual there. Well, there are a couple of interesting formulas in this chapter that I thought I would stop and mention. So one of them apparently is going to come up again in a later section, I think section 8, on L'Hopital's rule. Let me just say, some of the sections in James Stewart are really long. I'm too far into the game to use a different calculus textbook, but don't tell the publisher I probably wouldn't use James Stewart's textbook if I were teaching calculus. The sections are just too long. And I don't think they're arranged as well as they can be arranged. Again, I don't get to say because I'm not a math teacher, but I'm going to continue with James Stewart's textbook because I'm way too invested by now. But this relationship will become obvious when we get to L'Hopital's rule later on in the chapter. So the limit as x approaches infinity of the natural log of x over x to a power equals 0. So I just wanted to put it here because as long as that section is, we're going to need all the brain space we can have when we get there. This was an interesting one. This is from the problems. And Stewart, again, I don't. It's not against Stewart. I'm sure he's dead, so he doesn't care. But one nice thing I like about Stewart's textbook is that he introduces some little rich side notes from the history of math in the exercises. And the one he does here is the prime number theorem. And the prime number theorem basically says that the number of primes there are below a certain number is approximately that number divided by the natural log of that number. And James Stewart asks you to calculate, for example, about how many primes there are up to the number billion. So basically, you would take the number billion and divide it by the natural log of the number billion. And that would tell you approximately the number of primes. This theorem was suggested by Gauss, who was incredibly smart. He depresses me. This guy was so smart, man. But anyway, he came up with this, and it was proved about 100 years later. I think he lived in the 1700s, if I remember correctly. But the precise relationship is this, and I had to re-record this video because I didn't understand what this formula was saying at first. But now I think I've got it, by Jove. But basically and part of my problem is I was thinking that this was pi times n. That's not what this is. Pi here is the prime number function. And so the number of primes below, what this means is the number of primes below n is what this notation is saying. P of n, the number of primes below n, like a billion. Basically, that number is going to get closer and closer to n over the natural log of n as n approaches infinity. So as n gets really, really large, the number of prime numbers under a certain number divided by n over natural log of n is going to equal 1. These two are going to equal each other. So very fancy way of saying it, thank you. But it's really saying the same thing as this, that as n gets large, the number of primes below n is approximately n divided by the natural log of n. Well, you may not have cared about that. I don't think you necessarily need to know anything on this particular page, but I wanted to slip it in. Why not? And I hope you have a lovely day as we continue our journey through James Stewart's calculus textbook.